Alright, hello class. In this video we're going to start talking about the dot product, and specifically this particular lesson is going to be answering that question of, fleshing out the multiplication of vectors. Okay, so before we get started, I want to really drive on the fact about what multiplication of vectors is not. Okay, so there is no component-wise multiplication of vectors. And what I mean by that is if you have, say, the vector 2, 3, and you, say, want to multiply it by a vector, let's say 5, 4, and you do it component-wise, say 2 times 4 and 3, 2 times 5 and 3 times 4, which is the vector 10, 12, this is meaningless. Okay? Right? There is no practical definition, or there's no practical application of doing something like this. There's no mathematical or logical reasoning why this would happen, and we're going to talk a little bit about why that is, and it's just mainly because it's not really measuring much of anything. Okay, so let me show an example here. All right, so to show what these two vectors would end up doing, as we showed before, here's the u is the vector 2, 3, v here is the vector 5, 4, and if I do the vector 10, 12, we see that its direction maybe has something to do with these two vectors, but the magnitude is all out of whack. And so it's not really measuring anything useful. It's not measuring even the direction of the two forces acting together. Okay, so here in this sort of yellowish color, this is the resultant of u and v acting together, and we see that this multiplication guy isn't even matching the angle or the direction of the two vectors acting together. So this vector w doesn't really give us anything useful. It does give us a vector, but again, it's not practically interesting. It's not practically useful. Okay, so just keep that in mind as we go forward. This multiplying component by component and creating and spitting out a new vector actually doesn't give us anything. Okay, so let's talk about what some of these products are then. Okay, so as we talked about in one of our previous videos, is there vector multiplication? The answer is sort of. We've already talked about one of them, which was scalar multiplication, sometimes called the scalar product, which basically, if I'm multiplying a vector xy by a scalar, it scales the vector by that amount. Okay, this is the one that's done component-wise when you multiply by a scalar, so you're either doubling the vector, tripling the vector, cutting the vector in half. The one we're going to talk about next is the dot product. And the dot product, I think, mathematically is very, I don't want to say very simple, but mathematically it's pretty simple. So I'll just tell you right now, if you have a vector, let's say x1, y1, okay, and you dot it with a vector x2, y2, all right, all you do is you do take the components and multiply them together, However, you don't stick them in a new vector. What you do is you sum up these two values, right? So it's the x components multiplied together, the y components multiplied together, and then you sum them up. And you can extend this to 3 dimensions as you would expect. If you have, instead of vector x1, y1, z1, and you're dotting that with the vector x2, y2, z2, you take the x1, x2, x3, multiply them together. You take the y1, whoops, I don't know where the x3 came from, sorry. Take the x1 and the x2, multiply them together. You take the y1 and the y2, multiply them together, and the z1 and the z2, and multiply them together. Okay, so this gives us what is called the dot product. I mean, mathematically, like I said, it's not that complicated. It's kind of doing what we said we can't do, which is just multiply these things component-wise. But what is it? Okay, that's a great question, which I'm hoping we can answer here. All right, so a first explanation, if you've taken linear algebra, comes from that, because vectors are technically, we can think of them as, say, 1 by 2 or 1 by 3 matrices. So vectors are either 1 by 2 or 1 by 3 matrices. Okay, and you might think, well, if I have two vectors, v1 and v2, and I want to dot them together, well, you might think, well, we can't do that because in order to multiply matrices, the inner dimensions need to be the same, right? So I can't, apparently talking right at the same time, but I can't do a 1 by 2 times a 1 by 2. It has to be like a 1 by 2 times a 2 by 1. Well, how we get around that is technically with matrix multiplication. What we do is we say that it's v time or v1 times the transpose of v2. So using our matrix multiplication, we would say that this is x1 comma y1 times the matrix x2 comma y2. And following our matrix multiplication rules, again, if you haven't taken linear algebra, don't worry too much about this. We'll get into some other explanations, but it'll be x1 times x2 plus y1 times y2 in a 1 by 1 matrix. Well, 1 by 1 matrix is literally just a whole number, right? Or not a whole number, but a real number. It's just a scalar, okay? So that's the first thing that this comes from. But let's take it a little further and talk about it more in terms of like physical properties, what these physically give us. All right, so in a physical sense, physically, the dot product measures how much push or force one vector applies to another in its original direction. Well, okay, what do I mean by that? Well, if we go back to, say, our boat example that we did a while back, right, and it's traveling along, let's say, in the direction of vector v, and suppose that this boat is being affected by the stream. Well, if the current is pushing in this direction, then actually the vector is helping push along this boat. It should be speeding it up by a certain amount when they act together. And in fact, if you were to find the resultant vector of these two, just graphically, hopefully you can see that the magnitude of this resulting vector is larger. So in here, the current is pushing the boat along its direction. Okay, so here I'm basically saying that this current, even though it's not the exact same direction, it is close enough that the current should be pushing the boat helpfully, right, in its original direction. Okay, the opposite of this would be, let's say we have the boat traveling in its same direction, so we have V, but in this case, the current, which I'm going to put in red now, is pushing in an opposite direction. And as we might suspect, when we do it this way, if we look at the resultant, we're still sort of traveling in the direction we want, but this magnitude seems smaller. In fact, if we were to wrap this back around, yeah, it seems that our total speed will be lowered because of the current, because here the current is hindering our direction. It's pushing against our travel versus pushing with. Okay, so the dot product helps us measure this amount. Okay. All right, so it's basically, it gives us a number that helps us categorize the amount of push that one vector is giving to another, or the amount of energy one vector is giving to another, or what some people might consider work. If you've taken some physics, this probably reminds you of work, and it turns out the dot product helps us measure work. Okay, so how does it do this? Well, it does it in the following. All right, so suppose we have two vectors, v and w, and we can think of either v acting on w or w acting on v. It actually doesn't really matter which one is acting on the other. The dot product will give us the same number. Anyway, let's say there's an angle theta between v and w. All right, so if between these two vectors, I draw a line such that it goes from the tip of v down to w and does so with a right angle. Okay, what we have here is what's called the orthogonal projection. Okay, so the orthogonal projection, and the book goes into this in a lot of detail. I don't want to go into a ton of detail. We're just going to use this to help us establish this idea. But this orthogonal projection here, I've basically made a right triangle with a length parallel to w, okay, in as the base of this right triangle. So it turns out that this side adjacent here is what I'm going to call it. Well, that's going to be equal to the magnitude of v times the cosine of theta, since cosine is in terms of the side adjacent and the hypotenuse. So this side adjacent is going to be the magnitude of v times cosine of theta. Okay, so that's just the length. Okay, so if I called this new vector, let's say p for projection, that just tells us what the magnitude of p is. Okay, if I want to get the vector in the direction of w, I could just multiply, because this is a scalar here, multiply the scalar by the unit vector in the direction of w. So p itself is going to be the scalar, magnitude p, times the vector w over the magnitude of w. So this is the unit vector in the direction of w. Okay, but it's this magnitude I'm concerned with, because remember, the dot product gives us a scalar, and it looks like that this particular scalar would be the amount of push that v is giving w in its original direction. All right, so how in the world do all these things become related? Well, it comes from relating the cosine to the dot product, and we'll do it in the following way. We'll actually set up a non-right triangle and use the law of cosines. Okay, so this right here can be represented by v minus w, right? That's the other diagonal of the parallelogram. All right, and so from the law of cosines, we'll have that this length squared, so v minus w squared, is going to be equal to the magnitude of v squared plus the magnitude of w squared minus 2 magnitude of v magnitude of w times cosine of theta. Okay, now when we square a magnitude, I'm going to say that let's let v be the vector vx, vy, and w be the vector wx, wy. Now, if you have trouble following what I'm about to do here, don't sweat. We're going to get to the better explanation and, going from there. But for the people who want to see behind the scenes, how the sausage is made, this is how it's done. Okay, and then v minus w is, of course, the vector vx minus wx, comma vy minus wy. Okay, now, when we take the magnitude and square it, so remember the magnitude is the square root of the x component squared plus the y component squared, and then we're going to square this whole thing. So what ends up happening is just the whole square root thing disappears. So we'll get the same thing here. And I'm just going to jump straight to, it'll basically be vx squared plus vy squared. And we'll get plus wx squared plus wy squared minus this thing with the cosines. Okay, now the square root disappears and we just have these two things that we need to FOIL out. So I'll do that down here. It's just going to be vx squared minus 2vx wx plus wx squared plus, and here we'll get vy squared minus 2vy wy plus wy squared. And this is going to be equal to the same thing over here, so I'm not actually going to copy it down because we have a lot of things that cancel. Right, these vx squareds cancel, these wx squareds cancel, the vy squareds cancel, the wy squareds cancel, and we're left with a negative 2 times a negative 2 times a negative 2. So I'm going to go ahead and divide out that negative 2 from everything so that we end up with vx wx plus vy wy is equal to the magnitude of v times the magnitude of w times cosine theta. And this, the x components of v and w multiplied together, the y components of v and w multiplied together, that is the dot product that we just talked about. Okay, so it turns out that the dot product is the magnitude of v times the magnitude of w times cosine theta. Now, if we scroll back up to this, the v cosine theta, that was the side adjacent in this triangle that we created, the orange one. And then we scroll back down here. Oh, well, if we divide this magnitude of W over, so I'm going to square this off, but then down here, I'll say V dot W over the magnitude of W is equal to the magnitude of V times cosine theta. All right, there was that side adjacent that we discovered before. And notice that that gives us V dot W over magnitude of W. So V dot the direction of W. Okay, so this is what I mean when I say that the dot product, and if we go back to here, the dot product helps us measure the amount of push one vector gives to another in its original direction. Well, here's the direction vector. You can always think of unit vectors as direction. Okay, so the dot product helps us measure that. Okay, and you'll notice that with this cosine theta in here, which often this gets rewritten instead of in terms of this stuff, which I'm going to go ahead and get rid of for a second here. It's often written like this, that the dot product between two unit vectors is equal to just cosine theta, where theta is the angle between V and W. All right, where theta is the smallest angle between V and W. And what I mean by that is if you have two vectors V and W, there's a smallest angle and then there's a larger angle. We're not concerning ourselves with that, complication there. So it turns out that the amount of push one vector gives to another has everything to do with, well, the magnitudes of those vectors, along with the angle at which the two vectors interact. So how I think of dot products comes from video games, like racing games in particular, like Mario Kart or any of the arcadey racing games with boost pads. But you can think of it as also how how a say person is affected when they walk across like an escalator or like a moving platform, right? So we'll talk about that in a second, but let's talk about it in terms of like Mario Kart and like racing game. Okay, so suppose we have a boost pad sitting at a certain point on a racetrack, and we have a driver. Pick your favorite Mario Kart character, your favorite Crash Team Racing character, what have you, or whatever racing game you can think of with a boost pad. But what a boost pad does is in this case, it pushes you forward. So it's going to increase your velocity by a certain amount in this direction. But it really depends on what direction you approach it from. So if you hit it straight on, so if you come at it, you're driving around and then you come at it straight on, it's going to push you exactly. But if you come at it perpendicular, right, it's going to, say, push you sideways, even if you're still facing this way. So, and then if you drive against it, it's going to push you back. Okay? So, let's think about this. Let's say we have a driver who's hit the boost pad at an angle, I'll call this D for the driver, and it hits it at an angle theta. All right, and we're going to look at different possibilities. So let's say theta is 0. So the driver hits it dead on. Okay, so if I look at D dot B, I might have used some different letters here, but remember that's our magnitudes times cosine theta. Well, cosine theta is, in this case, going to be 1. So if we imagine this, d times 1 of b, well, what this tells us is that our driver gets 100% of the boost in the direction that they're driving. Okay? All right. Now, if I wanted to actually get that percentage, I would divide through. So that would be d dot b over the magnitudes, which would equal 1. Okay? When that angle, let's say, equals, let's do pi over 3, so 60 degrees. So suppose the driver hits the boost at 60 degrees. Well, now our dot product is going to be in terms of cosine of pi over 3, and cosine of pi over 3 is 0.5. So this comes out to be, I'll write it as the magnitude of d times 0.5 times the magnitude of b. So what ends up happening is that in this case, the driver only gets 50% of the boost in the direction that they're driving. Okay. All right. However, if we were to do something like 2 pi over 3, well, 2 pi over 3, that would be something like this, 60 degrees, but you're coming at the boost pad in the opposite direction that it wants to push you. We'll get, in this case, since we're looking in quadrant 2, our cosine is going to be negative. So we actually get negative 0.5 of the boost. Now what that means is we're getting 50% of the boost, but in the opposite direction. Okay, so it turns out, if you see on this side of the equal sign, these two things are always positive. Magnitudes are always positive. Therefore, the only thing that's going to make this side of the equation negative is the cosine. And so what that means is you only get a negative dot product if one vector is hindering the other. Whereas you get positive dot products when the vector is helping the other. All right, so if the dot product's positive, V is, say, helping W, so it's helping push W along. Where if we have a negative dot product, V is hindering W, pushing against it. And if you want to see that percentage, what you basically do is just divide out the magnitudes, or just look at the cosine of the angle. Now, if you don't know the angle, you can just divide to get that percentage. Okay, of how much boost we're getting, how much help we're getting. And if we're talking about 0, that's one thing we haven't talked about yet. Well, up here, if we look at the angle pi over 2, right, a 90-degree angle, that's what causes cosine to be 0. So this will make our dot product 0. And if you think about it, it's because if this was our boost, and we hit that boost at exactly 90 degrees, the boost still pushes us over, right? However, nowhere, right? So our actual direction and magnitude would change. However, it's not pushing us in our original direction at all. In this case, this is maybe completely horizontal, and then this is completely vertical, right? So how B pushes us, it does push us in towards the east, but we weren't traveling in the east at all. We were traveling due north. So we get no push in our original direction. It doesn't mean we're not getting pushed at all. It just means no push in our original direction. Okay, but it could mean that we're not getting any push if we get a dot product of 0. We'll get into that a little later, but basically perpendicular vectors have a dot product equal to 0. Okay? All right, so a 0 dot product essentially means that V is perpendicular to W, or one of the vectors is 0. Or what I call the 0 vector, which would be the vector made up of just zeros. All right, let's look at an example with some actual vectors here. So if I have the vector 3, 4 and the vector -5, 2, then their dot product mathematically is simple enough to calculate. We take the 3 multiplied by the -4, then we add the 4 times the 2. All right, so we're going to get -15 plus 8, which gives us -7 when we sum this up. So right off the bat, this tells me, I can just tell, if V is acting on W or vice versa, then that vector is hindering W, right? One vector is hindering the other in its original direction. All right, if we were to graph these, we can kind of see that. They almost look perpendicular, don't they? But not quite. Okay, so here is the vector that is actually perpendicular to W. I've called it B here in purple, just because for whatever reason it can, and this is why we need more tools than just graphing. But here's a right angle to W. So V, if V is acting on W, it is hindering it. It's pushing it away from its direction that it wants to travel in. All right, so that's how / why we get a negative value. Now, if we want to know by like how much, right, that sort of percentage idea, we can divide by the magnitude. All right, so let's calculate the magnitudes. The magnitude of V would be the square root of 3 squared plus 4 squared. So that would be 9 plus 16, which would be the square root of 25, which is 5, which I should have just seen that, but in this case I didn't. That's a 3, 4, 5 triangle. And then for the magnitude of W, it will be the square root of -5 all squared plus 2 squared. So we'll get the square root of 25 plus 4. So this will be the square root of 29. Okay, which I don't think comes out to be anything nice here. So now, if I were to take V dot w over the magnitudes. That would be negative 7 over 5 times the square root of 29, which is going to be... All right, so with my calculator, I got this as about negative 0.26. So you can think of v pushing w, or w getting about 26% of v's magnitude in its original direction, but backwards, okay? This might seem a little funky, but also one nice thing we get from this is we know that this is cosine theta, so we can actually get an approximation of the angle between these two vectors with cosine inverse. So cosine inverse of negative 0.26 is going to be our theta. Okay, so using my calculator, I got that this is about 1.83 radians, or it's about 105.07 degrees, which when we go back to the graph and look, that actually does make sense, okay? Because if this is 90 degrees, V is should be over 90 degrees away, which is exactly what we got. We got about 100, but not so far away that it's close to like 180. We still have a while to go before we get back to it being parallel again. Okay, so to give some words here, two vectors are orthogonal if v dot w is 0. That means that we either have perpendicular vectors or v or w, one of them is equal to 0. Now the 0 vector in 2 dimensions is just the vector 0, 0. You can think of that as just a single point, okay, as a vector. And if you think of it in terms of boost, if any vector v hits the vector 0, right, v dot 0, you'd get basically 0 out. So how much boost does this vector get? None, because what ends up happening is if somebody's driving around and hits this, bam, they've stopped. You can almost think of it as them hitting some brick wall or something. Okay, so that is the stop. Okay, now this doesn't often happen, but that's why we couldn't just say they're perpendicular. That's why we have the word orthogonal, because it does take into account this possibility. And here's an example to show how nice this is for three-dimensional problems, because this still works in 3D. If we have these two vectors, negative 2, 3, 1 and 3, 1, 3, when we take their dot product, right, I'll get negative 2 times 3 plus 3 times 1 plus 1 times 3. We get negative 6 plus, well, here we'll get 6, which is 0. So V is orthogonal to W. They must be perpendicular. Now, I know none of them are the 0 vector, so that means these two are orthogonal. They are perpendicular to one another. Okay, so here's a three-dimensional graph of these two vectors, and depending on how we look at it, it can be kind of tough to see, but they are indeed perpendicular to one another. Okay, so I find using the dot product a really quick way to tell. And again, depending on the angle, and that's what's tough about three-dimensional things, is it can be tough to tell what's going on using just a graph, but thankfully the dot product gives us a really quick way to tell if things are perpendicular using the dot product. Or finding the angle between two vectors in 3 dimensions, we can use the dot product. All right, so to wrap this all up, again, if as I mentioned before, if all this, like the amount of energy, the amount of push, the amount of hindrance or helpfulness that one vector applies to another, if that all sounded familiar, then it's probably because you've learned some physics. And it turns out that when a constant force F as a vector, but this vector would be in newtons, okay, is applied to an object producing a displacement, which would be in meters. In other words, we move an object. So if we have our force acting on an object and it causes movement, a displacement, okay, then the work done by this force is going to be just the dot product, F dot D, which if we know what the vectors look like, it's just going to be this. If we know what the magnitudes and the angle is, it's going to be this. Okay, and this, of course, is in joules, given what we have here. Okay, so to give an example of this, let's consider the following. Okay, so let's suppose that I have some sort of briefcase, right, sitting here, and I want to push it along using a force of, let's say I'm using, like I'm pulling it using a force of, I don't know, let's say 50 newtons. Okay, and I want to see how much work is done is if I pull it, let's say 20 meters. Now, here's the complication. Suppose that what I'm doing, whoops, okay, is I'm actually pulling the briefcase across the XY plane horizontally, while the force I'm pulling, okay, up diagonally. Well, it turns out that that's not really going to matter that much if I know what this angle is. So let's suppose that the angle that I'm pulling at is about 30 degrees. All right, so then the work is going to be F dot D. Well, I don't know these as vectors. However, I know their magnitudes and the angle between them. So it's going to be 50 times 20 times the cosine of 30 degrees. Right? So notice that it doesn't actually matter that much that I'm in 3 dimensions here. Okay? So this just comes out to be, okay, when I put it into my calculator, about 866.025 joules. Okay? All right, so we could have been given this problem instead as this. We could have been told, all right, this force here is, let's say 1, 1, 10, or actually let me not do it like that. Let's say it's like 2, 2, 3 is the vector for F, and then what we're doing here, since we're on the XY plane, I could say that this is going to be the vector 5, 5, 0, since we're not pushing it up into the Z, we're only pulling it along the ground. And we could, in this instance, find the work as just the dot product. Right? It'd be 2 times 5, 2 plus 2 times 5, plus 3 times 0, and we get 20 joules. Okay, but what this is saying is this vector here, we're saying that it's 2 newtons in the x direction, two newtons in the y direction, and 3 newtons in the z direction. And we're moving the object 5 meters in the x direction and 5 meters in the y direction and 0 meters in the z direction. So you'll notice that the force that we're pulling up doesn't really add to the work. Okay? However, that is easier than, say, getting on the ground and pulling by that force like level with the ground. Okay? So it's kind of like lost work, anything that's pulling up. So really, you'll want more of your force to be pulling left and right than up and down. Anyway, that's pretty much it as far as this particular lesson goes. In the next one, we'll look at our final type of products or multiplication when it comes to vectors, and then we'll start getting into what will hopefully be the new stuff in how we actually start applying calculus or approaching calculus with this. All right, see y'all next time.